In this video, we're going to talk about something called synthetic division, and it pertains to dividing one polynomial by another polynomial. So you may have seen this before as polynomial long division. This is essentially a condensed version of polynomial long division with all the redundancy removed. So there's a couple important points to remember about synthetic division before we even begin. First of all, and probably most importantly, it's easy and it's fast. Much faster than the polynomial long division to which it corresponds. And for that reason, a lot of people prefer it. Also, it only works when your divisor has the form x minus a constant, so like x minus 3 or x minus 2 or something like that. It will not work for higher degree polynomials, unfortunately. Third, make sure, and this is absolutely crucial, that if you are missing any terms in the polynomial, and we'll see this in an example, that you fill those missing terms in with 0. Synthetic division relies on zeros being placeholders, and it won't work correctly if you don't have those zeros there. So we'll see an example of that in this first example. So in this case, what we're looking to do is divide the polynomial f of x by two different linear polynomials. So here f of x is x cubed minus 5x minus 6. And in part A, which is the part we'll do together first, we're dividing that polynomial by x plus 1. And then in part B, we're dividing f of x by x minus 3. So the algorithm for synthetic division is very easy once you get the hang of it, but it's going to look a little bit nasty the first time I show this to you. Bear with me, I'll clean it up and I'll rewrite it again so you can see sort of all the things that you need to see. So first of all, notice that the polynomial f of x, which is x cubed minus 5x minus 6, is missing a quadratic term. What I mean by that is it's missing the x squared term. So you'll notice here that I filled in plus 0x squared to make up for that gap. That's absolutely crucial here. Also, in front of the x cubed, there's a hidden coefficient of 1 that I've written in explicitly here. What we're dividing by is x plus 1. So the first step in the synthetic division algorithm is to take that plus 1, that x plus 1, take that plus 1, change the sign, and put it in a box in the upper left-hand corner. And that's what you see here. The next thing that we're going to do is take all the coefficients on the terms of the polynomial and write them down in order. So in this particular case, 1, 0, minus 5, and minus 6 are the coefficients on x cubed, x squared, x, and the constant respectively. So here I've drawn you some arrows so that you can see where those numbers come from. The next step is to draw a line with some blank space in between underneath that line of numbers that we just drew. And then the first step in synthetic division is to bring that 1 down. That very first one, just slide it straight down below that line and write the number 1. The next thing that we're going to do is multiply what's in that box with that number 1 that we just slid down. We're going to take the result of that multiplication and push it up diagonally to the next space, which in this case is underneath the 0. And then we add down that column. 0 minus 1 is minus 1. And then we just repeat that process. We take the number in the box, negative 1, multiply by that new number below the line, which is also negative 1, and write that sort of diagonally up and right on the next line. So in this case, negative 1 times negative 1 is 1. And then once again, we add down the column. And what we get there is negative 4. That's negative 5 plus 1. Next up, we multiply negative 1 times negative 4, and we get 4, which goes in the next spot. And then once again, we add down the columns. So that gives us negative 2 at the end there. So I'm going to do this whole thing again without all that annotation so you can see what it looks like in real time. So I've set up the synthetic division once again. So we have that minus 1 in the box. 1, 0, minus 5, and negative 6 are the coefficients of our polynomial. First thing I do, slide that 1 down, take that, multiply what's in the box, and that goes on the next line. Add down the columns, and we get minus 1. Multiply that new minus 1 by what's in the box, which is also minus 1, to get 1. Add down the column to get minus 4. Multiply minus 4 times what's in the box, minus 1. To get 4. Finally, add down the column, minus 6 plus 4 is minus 2. Now we need to know what these numbers below that line tell us. And the last number here, in this case -2, is the remainder when we divide x cubed minus 5x minus 6 by x plus 1. And then we head up those numbers here. -4 is the constant coefficient in this case. The -1 next to it is the coefficient on x, and the final 1 on the very left-hand side is the coefficient on x squared. So it goes remainder, constant, x, x squared, x cubed, and so on down the line. So what we have on the bottom there is going to be the quotient, which is going to have x's and x squareds in it in this case. And the coefficients of the quotient are given by 1, -1, and -4 here. The remainder in this case is -2. Now the only thing that really remains here is figuring out how to write down our solution. And the way that we do that is going to be as follows. So we start out with x cubed minus 5x minus 6. That's the original thing that we were dividing here. So that's called the dividend. That equals the divisor, which in this case is x plus 1, multiplied by our quotient. And you'll notice here that the quotient is x squared minus x minus 4, where those coefficients are coming from that blue circle there. -4 is the constant, -1 is the x coefficient, and 1 is the x squared coefficient. And then finally the remainder sits at the very end. So once again, just a review of the terms that I've used here. The left side of the equality is the dividend. Next up is the divisor. That's the thing that we're dividing by. The quotient is in parentheses here. That's x squared minus x minus 4. And finally the remainder is -2. Now, the reason that we write things like this, the easiest way to justify this is to look at an analogy with integers. So if we look, for instance, at the number 44 and we want to divide that by 7. 7 goes into 44 6 times with remainder 2. Because 7 times 6 is 42, add 2 to that, you get 44. So the way that we write 44 is as the divisor, which is 7, times the quotient, which is 6, plus the remainder, which is 2. And it's exactly analogous on that last slide, in fact. Dividend equals divisor times quotient plus remainder. And it's exactly the same thing that you'll see in integers. So with that said, part B of this example was to divide x cubed minus 5x minus 6 by x minus 3. Go ahead and pause the video, give it a shot using synthetic division. You can go back in the video if you need to, and then come back when you're done and we'll go through the solution. So now that you've given this one a shot yourself, first thing that we do in synthetic division is put that 3 in the box in the top left corner. Next up, we write out our coefficients of our dividend. X cubed minus 5x minus 6 has coefficients 1, 0. You'll notice that I filled in that missing term there with a 0, minus 5 and minus 6. We slide that 1 down, multiply it by 3, that gets pushed up diagonal to the right, and then we add down the column. 0 plus 3 is 3. Multiply 3 times 3 to get 9, add minus 5 plus 9 to get 4. Multiply 3 times 4 to get 12, add down the column, minus 6 plus 12 is 6. Finally, the dividend, x cubed minus 5x minus 6, can be written as the divisor, which is x minus 3, times the quotient, x cubed minus 3x plus 4, plus the remainder. So you'll notice here that x minus 3 is exactly the same divisor that we had above. The quotient here has coefficients 1, 3, and 4 on the x squared, x, and constant term respectively, and those come from the bottom line, which I've outlined here in blue from synthetic division. Finally, the 6 is the very last number that appears below the line of synthetic division, and that's the remainder. So the nice thing about synthetic division is it's very, very quick. We can also use this to conclude some nice things about functions. And the first thing that we're going to talk about is called the remainder theorem here. So it turns out that if f of x is a polynomial and it's divided by the quantity x minus c, then the remainder of that division is f of c. In other words, you take that number c and you plug it into the function, that gives you the remainder. This is a really handy property to have. If we look back at that last example, part A, what we had found out was that x cubed minus 5x minus 6 was the divisor, x plus 1, times the quotient, x squared minus x minus 4, minus the remainder, which was 2. So on the left-hand side here, I have f of x. What this theorem claims, the remainder theorem, is that if we just take negative 1 and plug it into the function, and we run the arithmetic here, minus 1 cubed is minus 1, plus 5 minus 6 is minus 2, which is exactly the remainder that we got from doing the division. So notice the change in signs here. Our divisor is x plus 1, and if we change the sign on that plus 1 to get minus 1 and then plug it into the function, that will give us the remainder that we would get from the division that we did in the last example. It's a really nice property again, and we'll make use of this most often in the following corollary. So a corollary is an immediate consequence of a theorem, and in this case, x minus c divides evenly into the polynomial function f of x if and only if f of c is 0. Another way to state this, x minus c divides evenly into f and f of x if and only if c is a 0 of f. Very nice property to have. This guy is sometimes called the factor theorem. And this is a theorem that we're going to use pretty extensively throughout the rest of this chapter. And that pretty much does it for synthetic division. When you come to class, in the next class, we're going to use this to we'll go through some examples of this, and we're going to use this together with the things that we know about the zeros of polynomials to graph really general polynomials here.